Yes, okay, great. So without further ado, let's just jump right into it. So today's topic, today we're going to be covering the creation of a basic IFA antenna in FreeCAD, which is the inbuilt open source tool that CENOS uses for the geometry creation process. And we'll be making sure that the geometry that we have created is fully parameterized. So this means that if you change some sort of variable, it's going to affect the overall model as well. And it's very important to make sure that the geometry is properly constrained. So if you do not do some proper constraining of the geometry, you might get geometry that is somewhat out of place. And once you are done with the geometry creation process, you'll just head on to the physical setting setups. And once we have actually set up our parametric study, we'll be covering briefly the simulation results. And yeah, before we continue, what even is a parametric study? So the parametric study is essentially just applying a variable to a single or all of your geometry parts and varying it to see which one fits your desired results. It's an incredibly handy tool that eases your workload and basically allows you to ease the design process and focus on other things while the simulation runs. And so yeah, I've already started covering the benefits of the parametric study. So basically, you don't need to set up multiple cases and multiple instances of CENOS to do this sort of work. So you just create a single case and it runs each case consecutively. And this allows you to leave the simulation to run overnight or even over the weekend, depending on how many cases you've set up. And basically, this just allows you to easily find the best parameters for your RF model. And you'll see that in the presentation afterwards as well. And once you see the combined results, you'll see which subcase is the best one, and you'll be able to go back to the parametric workbench and open those results individually. And yeah, this basically just allows you to free yourself to do other tasks that you need in your RF engineering day. And so yeah, let's cover the general workflow of creating a basic case and setting up the parametric study. So the first thing you have to do is to create the case in CENOS and open up our geometry editor, which is FreeCAD. And then we strongly suggest that you start with defining the parameters that you need, but don't worry, you'll be able to add many more on the go as well. And once you define these parameters, you can start off creating your geometry and applying set parameters to that geometry. And once you've done with your geometry creation process, you just send that to CENOS and start all setting up the roles for your geometry and so on, and assigning the materials and before simulation, set up the parametric study. So you set up all the variables that you want to test, and once that's done, you just run the case. So the end goal for our webinar day one today is to basically teach you how to create RF models in CENOS from scratch, how to fully parameterize your model, and we want to simulate 5 different lengths of the IFA arm. So the longest part, which you can see on the image on the right-hand side. And basically, I hope you'll have a good understanding of parameterized geometry in CENOS. And so let's just jump right into it. So let me switch the visualization here. So I'll share my screen. And here it is. So those who are familiar with it, this is quite a familiar screen, but those who are not, this is the initial boot screen of CENOS, where you can actually see the basic 4 stages of the design process. But I won't delve in too much into that, as you'll be seeing that shortly as well. So let's choose a geometry source, which today is FreeCAD. And we're going to have to save a case, which I will gladly do. Let me do that right here. 0 webinar day 1. Press enter, and it's going to boot up FreeCAD for us. And once we're inside FreeCAD, we're greeted by the initial splash screen of FreeCAD, which is customized for our needs in the CENOS software. So as you can see, we have a selection of basic shapes from which we can choose from. We can do some basic Boolean operations by cutting or combining these objects into a single one. But this is not the thing that we'll be covering today. What we'll be covering today is how to create your geometry from scratch using the Sketcher workbench. So CENOS also provides you the ability to extrude your sketches and build geometry from that, which is infinitely much more easier than combining like a bunch of cubes. So before we do that, we have to set up some basic parameters. And we can do that by selecting the CENOS parameters in the tree view on the left-hand side, which is basically just a regular old spreadsheet, and it already comes preloaded with an example length, which we'll delete, and some basic instructions on how to use the parameters in FreeCAD. So let's start off by defining some substrate parameters. So we'll start with substrate length, and we'll assign some value to it. So basically what this does is that it applies an alias to this value that we have added here, which is the same as the one that we have written here in the name. So basically we'll have to call that once we actually want to assign the parameter somewhere. So let's add another parameter, which is going to be substrate width. Let's add 32 millimeters for that, and the substrate thickness, which will be making 1.55 millimeters. And so yeah, I'll quickly add in the other parameters that we'll be using today. Here they are. And once we've actually defined our parameters, we can just head on over back to the FreeCAD study and start creating our geometry. So once we're in the Sketcher workbench, which can be opened on the upper left-hand side, we can select Create New Sketch and add the sketch to whichever plane that we want. So I'll be adding it to the X and Y plane, and we are greeted by the Sketcher workbench here. So our substrate is going to be really basic. It's just going to be a rectangle. So I'll use the rectangle creation tool and draw a basic shape. So as you can see, we have a not constrained rectangle in the model, and I'll apply parameters to it. So we have the constraints toolbar up here on the right, and we have some basic parameters, tools for it. So we can make a point be in the same spot as another point, and so on, as well as some distance constraints, which I'll be using right now. So let's use the horizontal distance constraint here and apply it to this upper line here. And to apply the parameter that we defined in CENOS parameters spreadsheet, we just have to click on this small little button here, which is the formula editor. And then all we have to do is call the spreadsheet. So CENOS parameters, it's going to automatically add a point here. And afterwards, we have to call the parameter that we want to assign. And just click OK and OK. As you can see, the parameter that we defined before, so 44.8 millimeters, gets assigned to this horizontal length. Let's do the same for the vertical length as well. So let's add the CENOS parameters, substrate width. Press OK, and now we have a fully parameterized rectangle. But I don't like that this can be moved around the model, as I want it to ideally stay in the same spot. So let me use the coincidence constraint that I mentioned before. So I'm going to be selecting that tool and selecting a single point to which I want to place in a concrete spot in the model. So I'll select the bottom left point, and then I'll select the center of all three axes. So as you can see, our sketch has turned green, which means that it's fully constrained, which can be also seen on the left-hand side in the solver messages. So this is basically all that we have to do for the substrate in terms of the basic shape creation. And now, as you can see, we just have some sort of wireframe, and it's only called like sub new sketch. So let's change that. I'll call it substrate underscore sketch, just so I know what that is in the future. And let's extrude the sketch. And to extrude a volume from our wireframe, we have to head back to the part workbench, select our sketch, and find the extrude tool up here in the middle. So extrude the selected sketch, click on that, and let's extrude it by some arbitrary value for now, just to see how it looks like. Press OK, and as you can see, we have added a volume to our model. Let's rename it to something that we will remember in the future, in case you want to add some sort of like placement object or something like that, or an encasing. Let's call it substrate, and actually apply the parameter that we defined before, which is the substrate thickness. So let's click on the formula editor in the properties toolbar, length reverse, formula editor, and call the CENOS parameters substrate thickness. Press OK, and recalculate the object. And as you can see, we have our substrate. So the next part would be to create our conductive parts. So we ideally for the IFA need some sort of ground plane and basically the IFA structure itself, so the F letter. To do that, we have to go back to the Sketcher workbench, select the plane to which we want to apply the sketch, which is going to be this upper face here, and press on Create a Sketch. It's going to ask me if I really want to place it on that face that I've selected. I'm going to say OK, and we are greeted by the sketcher. So the first thing that we could do is define the ground plane. So to do that, we just have to add a rectangle again. In this case, I want the whole, I want it to be constrained to the upper edge here. So it's so there's no bare dielectric here, but it's covered by the conductive layer. And to do that, we can create an edge linked to external geometry. So what this does, it actually creates a sort of a construction line, which doesn't appear in the overall model, but it is fixed to this outer edge here, or whichever edge do we choose. So let's click on that and select the edge that we want to affix our ground plane to. So let's click here, and as you can see, a purple line appears. And let's use the coincident constraint again, using the upper point in the ground rectangle to that point. And let's do the same to the downward lower point. It's going to tell us there's a redundant constraint. That's because we have affixed a line to a vertical line, and it doesn't need what was this called? It was called the vertical constraint, which makes it a straight line and you can't bend it over. So let's delete that. And now the only degree of freedom that we have is along the x-axis. So that means we just have to apply a set length to this upper line here, which we'll do with the horizontal distance constraint again. And when I copied in the parameters, I copied in the ground length as well. So ground length, and press OK. And we have fixed our ground plane. So yeah, we'll use the same sketch to create our IFA arm as well. So to do that, we'll just add a bunch of rectangles. So first off, let's add the lengthwise, the larger arm of it. Let's add the shortening pin, which will fix to the right line of the ground plane. And we'll create the feed line as well. So I won't short this because I need it to be not shorted for the part definition. So right now, you can't see it, but here we have an extra line, which we don't need. So let's use the trim an edge with respect to a pick position and remove this line here. So let's delete that. Looks like I deleted a bit too much. So right now we have this line, which is under constraint. Also, we need to remove these lines in order to simplify our meshing process. So we'll use the same tool here. But now, as you can see, we have a bunch of these points which we don't need. So I'll extend the line that we have here, which is a leftover from our rectangle, and just delete that. And do the same for the horizontal line as well. And right now, we have simplified our model a bit. So let's do the same for these three lines here. So let's zoom in. Let's trim these off. And we can extend this line out so we can delete that as well. So much more simplified again. And let's start applying the parameters. Looks like we're good to go. So in order to do that, we first have to assign the trace width. So ideally, I want this line to be the same width everywhere that we have defined it. So let's use the vertical distance constraint and apply the value to this line here. So we're going to set the trace width for the shorting pin to be CENOS parameters, trace width. Press enter, and now we have fixed the length. And let's do the same for the feed. CENOS parameters, feed, trace width. And let's do the same for the arm as well. So CENOS parameters and trace width. Okay, that is definitely not it because we still have like 5 degrees of freedom. So as you can see, I can freely move these lines, which I ideally don't want because if I change one of these parameters, it might go basically haywire. So I have defined a couple of more parameters, which you can take a look back here. So we have some sort of matching gap, we have a feed gap, a short height, and the arm length. And let's define the short height first. So I'm going to define it as this highlighted line here. So let's select that, add the horizontal distance constraint, and call the parameters. And as parameters, shortening height, and voila, we have fixed our vertical length here. So the short pin still moves, which we can fix right now. So the formula editor is a pretty powerful tool in the sense that we can actually apply some sort of more complex functions with. So in this case, I want the gap here to stay a fixed length. And it is currently affixed to the ground plane. So what we can do is select this inner line here, use the horizontal distance constraint again. Apologies if this is not clearly visible, but should be good. Let's call CENOS parameters again and call the short height again. And as you can see, it is now basically shorted to the ground plane, which is not ideal. So let's subtract from it the parameter that I mentioned before, which was the feed gap. So CENOS parameters, feed gap, and now we have assigned some gap to the feed pin. So next up, we have the matching gap. So let's select the vertical distance constraint and apply that as well. So CENOS parameters, matching gap, and now it's some sort of fixed length. And last but not least, which is a quite important part, is the arm of the length. So let's select the line that we want to be the arm length. I'm going to choose this rightmost line here and assign a vertical constraint to it again. So CENOS parameters and arm length, which I have defined beforehand. So yeah, we still have some sort of degree of freedom. And as you can see, our sketch moves out of the substrate, which is not ideal. So this is the reason why we need to properly constrain our model. And we can easily do that by using the vertical distance constraint. But in this case, I won't be selecting a line, I'll be selecting 2 points within the model. So I'll select the bottom of the ground plane, so this point here, and the bottom of the shorting pin, so this point here, and apply the vertical distance constraint to it. So let's call CENOS parameters, and let's call the side offset, because I have defined that beforehand, and press OK. And we have assigned these values to our model. And currently, our model is fully constrained and is actually ready to be simulated. But let's do another thing that will be clearly evident in a bit. So I'm going to purposefully under constrain our model, and I'll be creating a line here. So as you can see, we have created this line in the middle of the ground plane. And the reason for this is that it'll help us define our port definition to be in the exact same spot that we want it to. So the next thing I would like to do is use the trim tool again. So I'm going to trim it, and now this line is freely movable again. And let's call the formula editor to fix this line into a fixed spot. So I'm going to be selecting the bottom point of that line and the bottom point of the ground plane and using the vertical distance constraint. And right now I'm going to have to call a bunch of parameters to use so we can actually fix this and make sure that this line moves as we move the, for example, the arm length of the IFA and so on. So let's call the first line, which is the side offset. CENOS parameters, side offset. And let's add, we have one trace of width here as well. So let's call CENOS parameters, trace width. So right now, if I press OK, it's going to place that line, the bottom part of that line down there. But let's not do that. Let's add additional parameters to it. I'm going to be adding the matching height, matching gap again as well. So CENOS parameters, matching gap. Now it's going to be a resulting 10 millimeters. And as you can see, it matches up at this point here quite cleanly. So I want to make sure that this line is the same width as the trace width. So I'll apply a vertical distance constraint to that as well. CENOS parameters, trace width. And now we have a set line adjacent to the feed. And that's basically it. So from this point on, you can extrude this sketch to simulate a 3D volume, but in the case of the simulation, it actually saves time to make this model as simple as possible. So simulate the conductive layers as 2D volumes to these 2D faces instead of to 3D volumes, as it makes the mesh less complicated. It makes the amount of mesh elements smaller, and it doesn't net you a loss in accuracy of the simulation. But first, let me rename this sketch to something that I'll remember. So conductors. And basically, we just have to select our model, everything that we want to send to CENOS, and click the Send to Geometry to CENOS button. So it's going to tell us that the geometry has been sent successfully, which means we can open up the CENOS app again. So once we have sent our geometry, we are greeted immediately by the geometry application screen. So in this case, we are working with the microchip/PCB design. So our IFA is that. And we can just select that, and we'll be greeted by our predefined roles. So in this case, every model that's in this application type consists of a substrate. So I'll select our substrate in the preview. Let's select our patch, which is a face. So I'll use the faces selection. Select that. Let's select our ground. And that is it. So last but not least, we have our port definition. So CENOS uses the thin wire approximation. So it uses a discrete port consisting of 2 terminals. So I'll have to select these 2 terminals in the model. So pick terminals, select the center point of the feed line, and now we'll be able to select the center point of the line that we defined in FreeCAD. So this is the reason why we actually created that line. So as you can see, we can see the endpoints of it and the middle point. And basically, we have set up our geometry of the case. And next up is the physical settings. So to do that, so to set up the physical settings, we just have to go to Physics. And here we are greeted by the simulation control. So we already see that we have the parametric study and some geometry variables. And let's actually start off with defining the materials. So let's go to substrates and assign FR4 as our substrate material. And the faces that we have assigned as ground and patch are already defined as perfect electric conductors. So that's done automatically. And our port definition is already preset as well at 50 ohms, 0 phase shift angle, and the port number. So here we will be actually selecting our frequency range, which we'll be selecting to be from 2 gigahertz up to 2.5 gigahertz. And we'll be simulating a step of 50 megahertz. And before we head into the parametric study, I would like to showcase the geometry variables. So if you have fully parameterized your model, or at least added some parameters to your model, you'll be able to change them here in the geometry variables. So if I change the arm length, for example, let's choose it to be, let's say about 20 millimeters, and press apply, as you'll be able to see in a moment, it also changes the model here. So basically, if you don't plan on adding anything to the model, you just want to change up the values in your model that you already created, you're just able to modify them using the geometry variables. And let's set it back to 28. I believe that is what we had before. Yes, that is correct. And let's just enable the parametric study. So from here on out, what we'll be doing is setting up our parametric study. And in it, we'll be able to assign pretty much any of the parameters that we have defined beforehand in FreeCAD. So in this case, I want to vary the arm length, but you are able to add as many parameters as you want. So if I add the matching gap, if you want to change the impedance of the model, I can do that as well. But in this case, let's just select the single one. And I can add as many cases as I want as well. So I can add 1, 2, 3, 4, 5. And I'll change the values to it accordingly. So I'll change the first one to 26, 26.5 for the second one, 27 for the third, 27.5 for the last one. And that's basically it. We have just fully set up our parametric study. And from here on now, we can just press run, and our case will be, run. But in this case, the way I have set everything up, it's going to take some time, and I'll just open up the results that we have already prepared from this exact same case. So once you actually press run, you'll be greeted by all of the S parameters of each and every subcase. So we have our 5 cases. So if you recall correctly, case 5 had the largest arm length. As you can see, we've reached about minus 14 dB. And the first case looks like it was our best one in terms of the S parameters, which is at about minus 18.5. And once you actually see the case that you think is the best for your use case, you can go back to the parametric workbench. So let me bring up the simulated case already. As you can see, everything here is the same that we had before. And we can just open up the parametric study and open up our individual results. So let me open up the worst one, which was 28 millimeters in length. But I already have opened the 26, which is here. And as you can see, the results you saw before are here in the full format. So you have your far field, your directivity, your electric field distribution. On the second slide, brought up. On the second slide, you have your Cartesian and polar plots of the radiation pattern. And on the last slide, you have your S parameters that you already saw before, your voltage to standing wave ratio, your accepted power of the antenna, and the reactance, resistance, and impedance. So yeah, let's take a quick look at the other one. So this is with the longest length. on the second slide, you can see the same things that we saw before, but as you can see, we have our different results. So our minus 14 dB at 2.25 gigahertz. And yeah, that's basically it. So that basically ends the webinar day 1. And thank you very much for joining. And if you have any questions, please raise your hand and we'll cover that as well. So yeah, if you have any questions, feel free to raise your hand and we'll already open them. Yes, Nick, go ahead. Nick, I can see you raise your hand, but I think your microphone is disabled.
Yeah.
Okay.
Apologies.
All good.
If you're simulating and processing is taking a while, is it possible to run CENOS in the cloud and take, say, an Azure VM and run it in the cloud, and for an hour or two? I don't want to buy a stonking machine just for the time it takes to simulate. Is it possible to move your license to a cloud computer and hire for an hour or 3 a stonkingly powerful machine?
Yes, definitely. So the way it works for the licensing, if I recall correctly, you are able to change your machine a certain amount of times, but if you do encounter a licensing issue, you could definitely contact us. Yeah. But yes, it is possible to simulate on a VM. However, you need to make sure that your VM supports OpenGL. If it doesn't, Paraview might not open, but that can easily be remedied by just opening the case on your personal PC as well.
Okay, thank you.
Okay, anyone else? Yes, Dixie, go ahead.
Hello there. We're having some problems when we get to the 3D simulation part. Obviously, you've got the 3D simulation on one side, and then you've got the antenna showing the electrical on the other side. The 3D simulation is shown at a distance. That's it, at a distance away from the actual antenna, so it's not sitting on the antenna.
Oh, so basically, the far field is not centered around any like conductive parts. It's just the antenna outline is just there for visual purposes. So it does not really reflect the actual placement on the antenna. It's just for visualization purposes.
Oh, okay, because it's quite far away. I mean, it's like a long way away. So they're very separate. So, okay. Is there any way to make it sit on the antenna?
Basically, yes. So in Paraview, you are able to move the far field by you can change the position of it if you want, over here on the left-hand side. However, I haven't done it in a while, so I'm not sure if I can easily do this. Yeah, as you can see, I've just slightly rotated it, and you are able to change the position if you want.
So it doesn't really tell me from where on the actual antenna that the kind of visualization would be coming from. It's not accurate to the antenna then, if it can be moved around. So
the orientation is accurate, but the exact placement, unfortunately, currently no. Okay. Sandy, maybe you can comment some more.
Yeah, sure. So the thing is that the far field is from the infinity. So like we're on the antenna, it comes from the far field. It doesn't really matter where you place the far field relating to the antenna in the visualization. So of course the radiation comes from the antenna, but you can't visualize it in this way since we're dealing with so big distances.
So what about the kind of near field stuff? Like, because we're dealing with small antennas and very small distances, so we kind of need to know where to orientate the thing that we're working on to the antenna, and where to best orientate the antenna to this item. And at the moment, we're getting the picture of the antenna, and then what looks to be, I don't know, about a meter away, you're getting this beautiful visualization of this multicolored donut.
Oh, so you would need to look at the angles of the far field. So if you look in the second plot, Rainer, if you put to the radiation patterns 2D views, you would probably want to start from the center. You know, look where the electric fields are the strongest in your antenna, and then go from there, and then check the angle and angle your antenna in the correct direction.
Okay, I'll have a go. If I can't get it to work as I'd like it to work, is it all right to get in contact with one or both of you?
Yeah, absolutely.
Excellent. Thank you very
Definitely.
much.
Feel free to contact us. We'll
right,
be glad to help.
Okay, cool. Thank you.
Yes, the recording will definitely be provided to each and every one of you who has joined the webinar, and should be to the people who haven't joined the webinar as well. But yeah, you will definitely get the recording once it's ready. So, any other questions? Alberto, unfortunately, I am not sure what you said there. And thank you to the first commentator for the very kind words. I'm glad you enjoyed the webinar. First day of the webinar. So if there aren't any other questions, I think we can end it here. So thank you everyone for joining the RF webinar day 1. Sorry.
Thank you. Yeah, thank you very much.
Yeah, I just saw a comment. But yeah, hope to see you all on the second day of the webinar. And again, if you have any questions regarding the software, you can send us an email or hit us up in the support chat, and we'll be glad to help. And so yeah, recordings will be sent, and see you.